Welcome back. This is a part two video of my presentation. If you haven't seen part one, I will leave a link to that video under the description part of this video. So today I'm going to walk you through two case studies. The first one is we are going to utilize a synthetic data set. And the second case study, we are going to look at a more realistic traffic data set. And in both case studies, we are actually looking at the vehicle velocity as the traffic state of interest. So in the first case study, this data set is generated by the Laxhoff method. And here I want to quickly shout out to Dr. Alexander Bayan at the University of California, Berkeley, his team for making this tool publicly available so we can generate this data set. So here, a quick note on the color scheme. So blue areas, bluish areas represent a higher vehicle speed, and the red zones are where vehicles are traveling slower with a higher amount of vehicle present on the road. And on the next two slides, we are going to see how PIDL and DL perform. So here, a little bit more explanations about what we are doing here. In this data set, there are approximately 400 vehicles present on this road segment. And we are assuming a scenario that in which 1% of this entire fleet are able to communicate with roadside units and transmitted data regarding vehicle speed. So in this case, you see those black dots, they're actually the vehicle trajectories. And you also see actually they concentrated in a few vertical zones. And that means these trajectories or those vehicles are actually in those covered areas by the roadside units. Because there is a limit on the communication range. So when a vehicle entered those gaps between roadside units, so that data was lost. We want to create this scenario to make this traffic state estimation application more realistic, although this practice did further reduce the availability of training data in our case. So what you are seeing here is actually 4 vehicles are transmitting their vehicle speed data. And those black dots are actually where the locations, actually this is a 2-dimensional coordinate system. So at what location, at what time that vehicle were able to transmit that data. And moving on to the next slide. So here we have a little bit more data. We are assuming like 10% of this entire fleet are able to transmit some data. So here we obviously see more data is available for training. And let's actually move on to see the tabulated results with respect to computation time and relatively error here. We do see actually PIDL will consistently outperform a regular deep learning neural network here in this case with exact same learning architecture. That's the same number of layers, same amount of neurons on each layer. So the PIDL, the unique advantage of PIDL of encoding the physics in this training process make it much quicker to converge and get the estimation output. So here, as you see in this table, those numbers or those results in the bold font indicates a better performance. And we also see actually PIDL achieved a better estimation in terms of accuracy in a shorter time as well. So here I just want to quickly recap what we learned from this first case study. Is we do observe the better or superior performances of PIDL comparing to DL, and also as the amount of available training data is increasing, we do see both neural networks evidently will converge quicker just based on the training inputs. So that's intuitively should be correct with regard to the training process of a deep learning neural network. So let's move on to the second case study. The second case study utilized the trajectory data that's collected in this NGSIM program. And the road segment is actually located in California. And the time period when this data set is collected is during the afternoon rush hour when people are like kind of leaving the offices at like 4 p.m. to 4:15 p.m. So what you see here when we can observe those slightly tilted but roughly vertical blue lines here, those are actually the shock waves in this data, and that indicates the congestion situations present on the road. And again, moving on to the next two slides, we will see how PIDL and DL will perform in this traffic state estimation task. Oh, sorry, before doing that, this slide, because this is a realistic data set, we need to first estimate the free flow speed and jam density. So here we use the linear regression and trying to get a sense of like, oh, what my VF value should be, what my rho M value should be. And I do want to point out that as you see, like rho M here, 0.2 vehicle per feet, that seems a relatively high value here. And that's just because this is a freeway, so that's the summation of all lanes here. So the majority of this road segment here will have 4 lanes, 5 lanes. So that's just summing all the lanes, vehicles on all the lanes together. So that's where we got the jam density here. And moving on here. So this is the first visual representation of like what PIDL and DL learned. So on the left side, so maybe on this figure, you will the reconstructions of shock waves maybe not that evident here in this case, but when we compare to the DL reconstruction on the right side, obviously didn't really learn much meaningful traffic pattern or meaningful output about the traveling velocity here. And moving on with a slightly bigger training data set here, now we can see actually PIDL on the left. We'll be able to capture that shockwave pattern and regenerate them. And again, on the left, sorry, on the right, the DL reconstruction will not achieve the same level of accuracy. Again, we will summarize the results here is actually when we do compute the relative L2 error of both outputs from the PIDL and DL neural network, we do see there's a huge difference in terms of accuracy that PIDL will get much better results, and that's visually verified by the previous two slides as well. Before we conclude today's presentation, I do want to take a note here and emphasize on the types of physical law that we are talking about here. So throughout this presentation, the physical law or the governing equation that we utilize is LWR conservation law, which is a hyperbolic PDE. And we do observe actually PIDL will perform much better on learning parabolic PDEs comparing to their hyperbolic counterparts. And what that means is actually, I'm going to show you, I'm going to demonstrate in the next few slides and see the differences between PIDL learning a parabolic PDE and a hyperbolic PDE. So here, what we are looking at is a ring road data, or like we test the PIDL neural network to learn a traffic density data set on a ring road. And here, this data set is actually provided by Dr. Rongye Shi at Columbia University. And we do see that given a portion of the boundary and initial observations, the PIDL neural network will be able to reconstruct this figure or this traffic density data set with exceedingly well. It's just when we see the ground truth and the reconstructed lines, they align with each other very, very closely, and we get a really, really low relative L2 error. But when we just slightly change this data and use a hyperbolic conservation law to generate this ring road data and also train a PIDL neural network with the corresponding conservation law or physics, we actually see there a lot of inaccuracy happening in those snapshots that's presented in the format of SAP figures here. And we do see a much higher L2 error in this case. So that's we want to take this note because that points out to the next research directions of PIDL. Like we want to investigate the relationship and further understand the reasoning behind actually PIDL performances with regarding to the hyperbolic PDE and parabolic PDE. But to summarize today's presentation, let me just talk about the advantage of PIDL in terms of applications transportation. I think the first advantage of a PIDL neural network comparing to its DL counterpart is actually the physics, the governing equations that we supplied in the training process will serve as a regularization agent in terms that it prevents the neural network from this overfitting issue, and that gives us a quicker convergence and better estimating performance or accuracy in this case. And the second benefit is actually, as we talked from the at the beginning of this presentation, we laid out the reasonings that why traffic observations or available training data can be very limited in this transportation domain. But the advantage of computing physics cost is actually the collocation point where physics cost is computed can come from everywhere in your data set in this X T two-dimensional space. And that's just because those are the points I want to verify if my estimation is complying with the governing equation or not. It doesn't matter if I have training data at that point or not. So that actually greatly expand the scope in which we can compute the cost terms. So that's the second benefit of utilizing a PIDL neural network. We do want to extend our gratitude to Dr. Rongye Shi at Columbia University for providing the ring road data, Dr. Animesh Biswas at the University of Nebraska at Lincoln for the LWR reconstruction of this ring road data. That you see the parabolic conservation law reconstruction of the ring road that was done with help from Dr. Animesh Biswas. We also want to thank Dr. Pushkin Kashro at the University of Nevada, Las Vegas for suggesting us to look at this about the types of PDEs that can make a huge impact in terms of estimation accuracy. Some references of our work, and thank you for joining me. That's the end of my presentation. I I appreciate you listening to me, walking you through some of our research work. And I look forward to seeing you next time.